Welcome to the Module 3 video for Introduction to Logic. So in this module, we will be learning truth value analysis. Despite what I said about at the beginning of the course, about logic being about analyzing the relationships between sentences, the way that I personally think of logic is it's kind of a game that we play with symbols on a piece of paper, right? And so up until this point, we've been learning how to represent statements as schemata. We've learned the meaning of our logical connectives. We've learned to avoid ambiguity, right? So we've kind of been looking at the board and the pieces for the game, right? So truth value analysis is the game that we'll be learning to play here. Everything that we will do going forward in the course ultimately reduces to truth value analysis, right? So this is incredibly important. Trying to go on in the class and succeed without knowing this would be like trying to master calculus without knowing how addition works or something like that. So this isn't very difficult, but it's very important that you get quite good at it. You'll have to do it many times on tests going forward. Right, so truth value analysis is kind of the game that we're playing, and we're going to learn the rules for doing it. Now, the official way to think about what we're doing here is we're testing for various properties, right? So first, what I'm going to do is I'm going to explain the properties of statements or schemata that we'll be testing for. So validity, consistency, and inconsistency, right? And then the last thing that I will do is I will explain truth value analysis and introduce the rules that you need to use to do it. It'll probably seem like there are a lot of rules at first, but one of the reasons why I wanted you to memorize the truth tables is that all of these rules kind of follow perfectly clearly from the truth tables if you've committed them to memory, right? So I don't personally at this point even remember the names of the numbers of the rules, but I have a pretty good grasp of the truth tables, so I can usually just figure them out on the fly. So again, please review your truth tables if you skipped that last week. If you don't have them committed to memory, I would go back and do that before proceeding with this module. But okay, so let's introduce the properties and that we're going to be testing for, and then learn how we're going to play our game. The first and most important property that we'll be testing schemata for is validity. And a schema is valid if and only if it always comes out true. True. So that's kind of all you really need to know. One restriction on all of these definitions is that we have to assign truth values to letters uniformly. So and you'll see what I mean by uniformly in just a second. So I'm actually going to demonstrate truth value analysis before I explain it to you, just so you can see that it's not really that scary. So there are a few examples of valid schemata that always come out true, that we can see that they're valid through really simple truth value analysis. So for the first example, I'm taking these from the book, so if you want to come back to this, you can look in chapter 4. The first example is of a valid schema is if P, then P, right? So we know that P is a statement, and we know that it can either be true or false, right? And again, the restriction up here about assigning truth values uniformly just means that we can't put true in for P in one place in the same branch, and in another branch put or in the, sorry, we can't, if we assign true to P, we have to assign true to P everywhere in that branch. Okay. So there are two possibilities for P, right? It can be either true or false. So true, if true, then true, or if false, then false. Oh, that's awful. Right? And if we look at our truth table for the conditional, we see that if the antecedent and the consequent of our conditional are both true, the whole conditional is true, right? And if we look at the truth table for our conditional again, we'll see that every conditional with a false antecedent is true, right? So this schema, if P then P, is valid, right? Because no matter how we assign the truth values, so long as we do it uniformly, right, it'll always come out true. So let's just take a look at another example, and this is one you've already seen, the second example of a valid schema. So let's consider the schema not P or P. Right, so again, we have to assign our truth values consistently, and again, there are only kind of two options. P can either be true or it can be false, right? So if we assign true to P, we get false or true, right? Because if P is true, then not P has to be false. Or if we assign false to P, we get true or false. Because if P is false, then not P is true, right? And if we consult our truth table for alternation, we will see that an alternation comes out true as long as one of its components is true. And so because no matter how we assign truth values to P here, as long as we do so uniformly, we'll always get one component to come out true. This schema is valid. It always comes out true. Okay, I'm going to give you a little bit more of a more complicated example that has more than one letter. So the third example of a valid schema that I'm going to give you is if P, then, and we will be using dots from here on out, so get used to them, P or Q, right? So how I'm going to do this is I'm going to assign all the values to P and then see what we get left with, okay? So there are two options, right? We can get true. If true, then true or Q, right? Or, whoa, what happened there? Or the conditional where the antecedent is false, false or Q, right? And again, all we're doing here is just let's assume that P is true on one side, let's assume that it's false on the other side, right? Because if a schema is valid, it's going to always come out true no matter what the truth value of P here is, right? So the right side's actually really easy. We should know by this point that a conditional with a false antecedent, and this whole schema as a conditional, right, is always going to end up true. So we can just write true here. It doesn't really matter what the truth value of P is, right? So on the left branch, right, well, let's look at this alternation, true or Q. Well, it's an alternation and one component in it is true, right? So we know that this the whole right side, the whole consequent of this conditional is going to end up true. So we can reduce it like so. If true, then true, right? And if we look at our truth table for the conditional, we will see that conditional with a true antecedent and a consequent will be true. So this is a valid schema, right? It's true, you know, regardless of how we consistently assign truth values to each letter. And actually, as it turns out, we don't even need to worry about the truth value of Q in this one. The structure shows us that, you know, the P alone, right, is sufficient to make it true. So those are three examples of valid schemata. Draw a line there. Again, I will explain the process for doing this truth value analysis later, but I just want to give you some examples and hopefully you understood that. So let's move on to the next property, consistency. So a schema is consistent if it comes out true at least once. And again, I'm not going to write it for every definition, but that means under a uniform assignment of truth values to each letter. So you've already seen a bunch of consistent schemata. The simplest example is P, right? Well, P is a statement, so it can either be true or false, right? That's how our analysis of it would run. And because it comes out true in at least one case, it is consistent. One thing that you might want to know is that all valid schemata are consistent. And if you think about that, it should make some sense, right? If a schema is always true, then it's going to be true at least once, right? So let's look at another example of a consistent schemata. This is example 2 from the book. So P or Q, right? So let's just start with P, right? So we make a branch, so true or Q, right? Or false or Q, right? So we know if we look at our truth table for alternation that the left side's just going to straightforwardly reduce to true, right? Because we have one true component of an alternation, and as long as we have one true component of an alternation, then the alternation as a whole is true, right? So over here, it's a little more complicated, right? So we have a false component of an alternation. So the way to think about this is that, so you have a false component of an alternation. You want to know whether or not the alternation as a whole is true or false, right? Well, the whole alternation, if it's an alternation of two things and one of them is false, the only way that it can be true is if the thing that we have left is true, right? So we can just drop this false from the alternation. We get a Q, right? And, well, Q is a statement. It can either be true or false, so true or false, right? So this schema is consistent as well because it comes out true at least once, namely twice. Okay, let's look at a more complicated example. So we have the schema, third example from the book. If P, then Q and P, right? Again, just, for your edification, if you're still in pain from the dots, this is the same thing as this, right? You have to get familiar with the dots. I encourage you to do so, but just in case you're confused. So again, you probably getting the gist of how we do this. Well, we have more P's than Q's, so let's plug in the P's. Or plug in the truth values for P. So we can have either true, therefore Q and true, right? Or we can have false, therefore Q and false, right? So this whole statement 3, the whole big schema, is a conjunction, right? So let's look at the right side. So we see on the right side that we have a conjunction, and we have a conjunction where one of the sides, namely, this side is false. And we know that a conjunction is only true if all of its components are true, right? So we know that this side's going to be false, right? So what do we do over here, right? So again, the whole thing's a conjunction, and we want to know whether or not it's true. And we know that conjunction is only false if at least one of the components is false. So what we can do here is we can ignore this, the true right here, right? Because we want to know whether or not it's going to be true or false, and a conjunction is only false if at least one of the components is true, so we don't have to worry about the true components. We can just get rid of them, right? So that leaves us with true, therefore Q, right? So remember, if we look at the truth table for the conditional, we will see that the only case where the conditional is false is where the antecedent is true and the consequent is false, right? And if we really think about that and try to appreciate what it means that if we have a conditional where we know the antecedent is true, well, then the truth value of the whole conditional is going to be whatever the truth value of the consequent is, right? Because if you look at the truth table again, you'll see that a conditional with a true antecedent and a true consequent is true. A conditional with a true antecedent and a false consequent is false, right? So if we have true in the antecedent spot of a conditional, we can just ignore it, get rid of it. It leaves us with Q, and since Q can either be true or false, right? That's the end of our truth value analysis, and we see that it comes out true at least once, right? Remember, schema is consistent if it comes out at least once. Came out true at least once, so it's consistent. We'll now look at our next logical property, inconsistency. The final property that we'll be testing our schemata for is inconsistency. And a schema is inconsistent if it never comes out true. Again, provided that we uniformly assign truth values to each letter, right? Two important facts that you ought to know about the relationship between inconsistency and validity. The first is that the negation of any inconsistent schema is valid. And that shouldn't be that crazy. If a valid schema always comes out true, well, you put a negation sign in front of it, flips the truth value, right? It's going to make it always come out false, right? Similarly, if you have an inconsistent schema that always comes out false, you put a negation sign in front of it, it'll always come out true, right? The second thing is just that the negation of any valid schema is inconsistent. And again, let's just look at a few examples of this, right? So you've already seen one of them, and one of them is the conjunction P and not P, right? So let's do what we've been doing, plug in all the possible truth values for this. So if P is true, then not P is false, right? If P is false, then not P is true. These are both conjunctions. If we look at the truth table for conjunction, we again note that a conjunction is only true if all of its components are true. We have false components in both of these, right? No, bad. See, false and false. And so we know that these, both these branches are going to reduce to false, which means that this conjunction never comes out true. It's inconsistent. Right, so another example, again, I'm just taking these from the book, so you can go reference what I have there if you want to see it written out all pretty, is the negation Q or not Q. Right, so if you've been paying attention, it should be pretty clear that the part of the statement that's inside the parentheses, Q or not Q, has to always come out true. It was one of our examples for validity above was P or not P, right? So if we change the letter, it doesn't change anything. So let's plug in our truth values. So if Q is true, then not Q is false, right? Similarly, if Q is false, then not Q is true. And if we look at our truth table for alternation, right, we see that any statement, any schema there's an alternation that has at least one true component is true, right? Both of our alternations on these sides have at least one true component, so we get not true, not true, right? And if we look at the truth table for negation, we see that the negation of any true schema or statement is false. So false, false. I had another example in the book, but it's really big and hard to fit on a page, so I'm just going to skip that. So these are the three properties that we'll be testing for. Validity, schema is valid if and only if it always comes out true. Again, provided that we assign the truth values uniformly. Consistency, a schema is consistent if it comes out true at least once. Again, all valid schemata are consistent. And inconsistency, a schema is inconsistent if it never comes out true. And again, important facts. And by important facts, I mean I'm almost certainly going to give you both of these or some variation of them on a test. Right, the negation of any inconsistent schema is valid, and the negation of any valid schema is inconsistent. So those are our three properties. Now we're going to learn truth value analysis. We're going to learn how to play our game to test for these properties. Okay, welcome to the last part of the Module 4 video. And in this part of the video, I'm going to explain what truth value analysis is. So truth value analysis is the method that we will use to test our schemata for the properties of validity, consistency, and inconsistency. Now, I like to think of this as kind of a game. And full disclosure, actually, I don't think logic is terribly useful for the sort of things that we do exercises for in a typical logic book. It is useful. But I like to think of it as just kind of a game that we play with symbols on a page, right? So up until this point, with our well-formed formulas and our logical connectives and our truth tables and our example of schemata, we've kind of been looking at the board and the pieces for this game that we're going to play. So truth value analysis is where we learn the rules and we actually start to play the game. So it's very simple to do this. If you don't worry too much about, the details of why all this works or whatever, and you just think of it as a game for kind of reducing things, I think you'll find it pretty easy. So I'm going to explain truth value analysis, right? I'm going to then go over kind of all the rules that you need to use it. You'll get the hang of the rules probably halfway through my explanation, and therefore you'll probably get bored. So I'm going to explain the truth value analysis first, and then I'm going to go through all the rules. You can find all of the rules in Chapter 4, and I'm going to send out a handout that just has them listed for your convenience, right? So let's get to it. So truth value analysis. Oh, by the way, I apologize. I thought I recorded a bunch of this, and I forgot to hit the record button. So a bunch of this is pre-written. I hope that is okay. Okay, so truth value analysis. There are two steps. We just apply step 1, then step 2, then step 1, then step 2 repeatedly. It's really easy to remember. So the first thing that you do in truth value analysis is you choose the most frequent letter in your schema, and you assign to it every possible truth value. Right? And the way that we do this is we make a different branch when we assign true to it and when we assign false to it. So if we look at our schema, if P then Q, right? So on the left branch, we've assigned true to P. We could have picked Q. They occur with the same frequency. I just picked P because it's first and comes early in the alphabet, I guess. Right? In our right branch, we've assigned false to the letter P, right? So those are the two possibilities for P. P can either be true or it can be false, and we make a branch for each way of assigning the truth value to it, right? So that's step one. So we can't reduce this anymore, right? So we have true on one side. As soon if our truth value analysis terminates in a single true or a single false in one branch, then we're done with that branch. But what if it ends in a letter, like Q here? Well, what we do here, the only thing we can do is go back to step one, choose the most frequent remaining letter, I guess, and assign to it every possible truth value. So the way that this looks when it's finished is like so here, pay attention to the way that this looks. So we can't apply any reduction rules to Q. We don't have reduction rules for a single letter. I promise you there aren't any. So we just repeat step one. We make one branch with true, one branch is false. All of our branches for our entire schema have ended up in either true or false. So our truth value analysis is complete, and we can see that it is a consistent schema. It's not valid because it comes out false at least once. It's not inconsistent because it comes out true at least once. It's consistent. Okay, so what I'm going to do now is I'm going to go through the rules. And again, if you get bored, you can skip to the end of the video where I'm going through many examples of truth value analysis, right? But so here is the first rule. And the first rule is delete true as component of conjunction. And again, if we look at the truth tables for conjunction, this should make sense, right? A conjunction is true only if all of the components are true, right? And so if we consider, to take the simplest possible case, the conjunction true and P, right? So we know that the whole conjunction true and P is going to be true only if all the components are true. Well, we know this true is true, right? So the whole thing's only going to be true if P is true. So we just delete that true, right? So here are some examples of how this works, right? So for the first example, example one, right here. Right, so we have, we've reduced schema and we get true and Q and R and not S. So we drop true as a component of conjunction, goes to Q and R and not S. So the second example, right, so this is a conjunction. The whole scheme is a conjunction, and that dot here gives us that a clue that it is. And so again, it's a conjunction of P or Q and true. And to delete true as a component of conjunction, we just get rid of it. We arrive at, P or Q, right? So another example, right? This is also a conjunction. I know that it's in dot notation and you're still probably getting a little used to it, but the groups, the big groups are this and this, right? It's the conjunction of this whole schema and true, right? So if we wanted to drop T, or true as a component of conjunction, we just get rid of it, and that's what we're left with, right? Again, not rocket science. Okay. Zoom. Okay. So the second rule is to delete false as a component of alternation, right? And again, if we were to look at the truth table for this, it would make a lot of sense that we could delete false as a component of alternation, right? An alternation is only true if at least one component is true. So if we consider, a really simple case, P or false, right? Well, how do we know whether or not the whole schema is going to come out true? Well, it's only going to come out true if P is true, right? So the false just doesn't matter to us, right? It's only going to come out false if P is false. So if we have an alternation where one of the halves is false and we're applying our reduction rules, we just get rid of it. That goes to P. So some more worked out examples. Consider this first one, right? So false or Q and R, right? So what we want to do is we see that the first component of this compound statement is an alternation, right? It's false or Q. If we drop the false, we get Q and R, right? And so the dot here isn't really signifying anything except conjunction, and it means the same thing as this. You don't have to rewrite it like that, but it's a little neater and cleaner, right? So second example that we have is this ginormous alternation. So we can see that it's an alternation, right? Because this is one side, this is the other side, and we have an or there, right? And so to drop or delete false as a component of alternation, we just get rid of this side, and this is what we're left with. Okay, one more example. This is a big ol' alternation of conjunctions. So we have P and Q, or R and Q, or not P and R, or false. And so what we do is we just drop that false, and that leaves us with this. So that's how we would apply that rule there. Okay. So rule 3. Now I've caught up to the stuff that I thought I recorded. So you reduce a conjunction with false as a component to false. Right, and again, if we look at the truth table for conjunction, that should be pretty clear. We know that a conjunction is false if any one of its components is false, right? So to use, first really simple example, consider the conjunction P and Q and false. Well, if we wanted to apply our reduction rule here, we would get, we know this is a conjunction. We know conjunctions only true if all of the conjuncts are true, and false if at least one of them is false. We got at least one of them false here, so the whole thing goes to false, right? Let's look at another example, a little more complicated. Part of the point of these complicated examples is to get you used to dot notation, just by the way. So P if and only if not Q, therefore QR or P. Oh wait, sorry. I need another dot there. There's a typo in the book. And false. Right? So this whole thing is one giant conjunction. See, we have the double dots here. We know double dots anywhere else. It tells us that it's a conjunction. We know that any conjunction with at least one false conjunct is false. So this whole thing reduces to false. So one final example here. Let's look at PQR or not Q, not Q and S, and false. So again, this whole thing is a conjunction. You see, this is the one group, this is the other group, the big groups anyway, and it's a conjunction that has a false component to its conjunction, and so we reduce the whole thing to false. Okay. So rule 4 is to reduce an alternation with true as a component to true. Right, so again, if we look at the truth table for alternation, this should make perfect sense to us, because an alternation is true if at least one of its components is true. So if we got true for one component of our alternation, we know the whole thing is going to be true. So the simplest example, something like P or true, well, it's an alternation. One of its components is true, so the whole thing is true. Let's look at another example. Oh man, I was brutal with some of these are really long in the textbook. P, this is a little easier. P or Q or R or true, right? So this whole thing's one giant alternation. It's an alternation with at least one true component. So we reduce the whole thing to true. I'm going to skip the third example for that one. That's a lot of writing. Okay. So rule 5 tells us to drop true as the component, or drop true as antecedent of a conditional. Right, so again, simplest example, just real quick, first example. Say we got true, therefore Q, right? So we look at the truth table for the conditional, right? When is the conditional false? Well, the conditional is only false if the antecedent is true while the consequence false, right? So that tells us that if we have a true antecedent, the whole conditional is going to be true if the antecedent is true, and false if the antecedent is false. So to apply this rule to this one, we reduce true, therefore Q, or if true, then Q, to Q. Right? Another example here is if we have a schema like this, where the whole thing is a conjunction, but one side is a conditional. So P or Q and true, if true, then Q, right? How we would apply this? Well, the right side's a conditional. It has true as an antecedent. So we'd get P or Q and Q, right? So one more, maybe slightly more complicated example is, though honestly, each single application of the rules is almost mindlessly easy. This is very, very simple. Don't get thrown by the fact that some of these are really like long. Okay, so we have true, if true, then not P and Q, not R, or PS. So the whole thing, our dot tells us, is one big old conditional. And it has true as an antecedent, so we drop the antecedent, and that leaves us with not P and Q and not R, or PS, right? Cool. So rule 6 tells us to reduce a conditional with false as an antecedent or true as a consequent to true. And again, if you look at the truth table for the conditional, that should make perfect sense, right? Because any conditional that has false in the antecedent spot or true in the consequent spot is true as a whole. So just a few simple examples of how to apply this rule. So first one is just going to be false. If false, then P or Q. Well, we know that a conditional with a false antecedent is going to be true, so it's true, right? Another kind of variation, the second way of applying the rule, let's consider P or Q. It's true. Right, and again, if you look at the truth table for a conditional, every conditional with a true consequent is true. So we reduce that to true. I don't want to write out the last example. Some of these are too long. Okay, so our seventh rule tells us, and this is maybe a little tricky, that if a conditional has false as a consequent, reduce the whole to the negation of the antecedent. And I think if you did look at the truth table for this, it would make some sense, right? Because, well, let's imagine that a conditional has a false consequent. Remember, the conditional as a whole is only false if the antecedent is true or the consequent is false. So, you know, we reduce true, therefore false. That's always going to come out false, right? That's the only way a conditional comes out false. So if the consequent's false, right, the only way for the conditional as a whole to be true is if the antecedent is false, right? Again, this is the part where I'm like, don't worry too much about whether or not this really captures what we mean by if-then in ordinary English, right? So just some really simple examples of how we might apply this rule. So first, let's consider if P, then false, right? Well, okay. We have a conditional with a false consequent, so we reduce this to not P, or we could write it with the bar over it, not P, right? So another slightly more elaborate example is P or Q or R, and then therefore false, right? So here again, we have a conditional with a false consequent. So we reduce it all to the negation of the antecedent like so. And here we have to use the negation sign and parentheses, P or Q or R, right? Because this, this negation of this alternation does not mean the same thing as not equal to P or Q or R. You'll, in a few chapters, you'll understand why they're not equal in a very clear manner. But for now, just know that you have to, in a schema like this, when you negate the entire antecedent, you have to put it in parentheses if it's one big group and not just a single letter. Okay, so one more example of how to apply this rule. 3. Let's say that we have not Q, therefore false, and not R and S, therefore false, right? So this is a conjunction of two conditionals, each of which has a false consequent. And so we can apply this rule twice at once if we like. I will always allow you to take reasonable shortcuts. I've seen, 10,000 of these in my life. I will be able to pick up on it. So how I would do this is I just apply the rule to both sides of the conjunction at the same time, and that would give us not Q, right? If we want to negate something that's already negated, we can put another negation sign in front of it, and not RS. So one thing that should be pretty obvious, if you say not Q, you're saying the same thing as Q, and if you say not RS, you're saying the same thing as R, or not R and S, you're saying the same thing as R and S, right? So these two are equivalent to each other. You can just automatically drop the double negations if you want. You don't have to, but again, it just saves you some time to write some stuff. And actually, we could rewrite that as just QRS if we really wanted to, because again, this dot isn't really doing anything here. We just have a conjunction, right? Okay. So there's like one more, right? Yeah, there are a few more. Okay, sorry. Look at my notes. So we have rule 8, right, which tells us to drop true as a component of a biconditional able to use the rules on every learning practice going forward. You'll be able to use them on the final exam as well, but I would start just trying to get these down. And the way that I would do that is I wouldn't try to like make flashcards and memorize the rules. I don't think that's so useful. Is what I would do is I would just try the exercises with a rule sheet in front of you, right? And I think you will, before too long, just start to be able to apply them like reflectively without thinking about it. So what I'm going to do now is I'm just going to show you some examples of truth value analysis that'll hopefully make it a little clearer as to how you're supposed to do it. Okay, so what I'm going to do now is I'm just going to make up a bunch of examples and do them. So how I'm going to do this, I'm going to do truth value analysis on them. How I'm going to do this is I'm not going to cite each rule because I would have to scroll up. I will explain in English what I'm doing. Analysis, right? If you really want to see an example with all of the rules cited, I think there's at least one long one worked out in the book. And if you're desperately confused when you're trying the homework problems, you can send me an email and I will send you like a video or post a video of me working through it while I'm citing the rules. It just isn't, you'll get the hang of these so fast, or at least 99% of the students do when I teach this class, that it's almost not even worth remembering which number's which, right? So let's start with a really simple schema. So Q and R, right? So here we have Q and R, it's a conjunction. We have one Q and one R, so all the letters occur equally frequently, right? So I'm going to pick Q just because it's there, right? So true R and then false R, right? So we've done the first step of truth value analysis. We make the branches and we assign each truth value to one letter at a time. So since it's a conjunction, right, the right branch is the conjunction of false and R. We know from both our truth tables and our rules at this point that if a conjunction has a false component, the whole thing's false. So reduce it to false, right? For the left branch, it's true and R. If you remember our rule above, we drop true as a component of conjunction. So that leaves us with R, right? And then we've reached a single letter, or we can't apply any more of our reduction rules. And so R can either be true or false. And that's our truth value analysis. And it shows us that this schema is consistent. It comes out true at least once, and it is not valid because it doesn't always come out true, and it is not inconsistent because it does come out true. Okay, let's look at a little bit of a longer one. So, but some of these might be pretty close to the ones I gave you on the exercises. Please try them, even if they're similar in form. The reason for that is just like you need to practice these. So let's look at A, if and only if, B, if and only if, what do I want to do here? Let's go B, therefore A. Okay. This is a little more complicated, which is good, actually. And again, this is the main operator here is a biconditional, right? And the two big groups are... Actually, wait, I'm going to rewrite it like this with more dots just to be clear. This is what's going on. It's the same thing. It just looks cleaner. Okay, so let's get to the truth value analyzing. I'm going to end up zooming in on some of these because it can get kind of long to write these out. So we have two A's and two B's. No letter occurs more frequently than any other letter. So again, I'm just going to pick A for the fun of it. Right. So true, therefore B, and, or if and only if, B, therefore true. right? So which of our rules can we apply here? Well, there are a few. So we can apply one of our rules concerning a conditional and one of our rules concerning a biconditional. So the first thing I'm going to do is I'm going to apply one of the rules concerning our biconditional. So we drop true as a component of a biconditional. So that gives us, and remember, I'm going to apply it, just to be clear, to this component, right? So that gives us B, if and only if B, therefore true. Okay, so now we can apply one of our rules that's concerned with the conditional, right? And, well, what's the rule that we can apply to our conditional? Remember, we reduce a conditional with false as an antecedent or true as a consequent to true. So we reduce that to B, if and only if. We can keep the dots in if we really want to. True, right? So what else do we do with this branch now? Well, we have a biconditional, so we need to use one of our rules for a biconditional, right? And what we do when we have a biconditional with true as a component is we drop true like we did up here, right? So that gives us B, right? And B can be either true or false. Now let's look at, I'm just going to draw a line to make it clear where the branches start and end, right? So we started with A, we made A true over here, so we got to make it false over here. So we do false if and only if B dots, if and only if B, therefore false, right? So again, we could apply two rules here. One of them's for conditionals, one of them's for biconditionals. So the first rule that I'm going to apply is going to do it kind of the same order. I'm going to apply the rule here. So if we have false as a component of a biconditional, we drop false and we negate the other side. So this would go to not be if and only if B, therefore false, right? So again, we're stuck with a conditional, right? And what do we do with a conditional that has a false consequent? Well, we apply our seventh rule, which is if a conditional has false as a consequent, you reduce the whole to the negation of the antecedent. So we reduce that like so. Not B. And I can just promise you that this is going to come out true, right? You could substitute, you could branch it again, right? So if you really wanted to be super thorough, the right thing to do would be to do, so let's sub in true for B, which gives us false, therefore false. And then if we put in false for B, that gives us true, therefore true. And we could do the reduction rules. You know, we could drop the true here and drop this and negate the other side. But remember, a biconditional is true if both sides have the same truth value. And if they're literally the same thing, they'll always have the same truth value. So we can just end that there. And that is the truth value analysis of that. So let's go for another example here. I'm just making these up off the top of my head. So for the third example, let's do like A or B and not B, therefore A. And again, I'm using more dots than I technically need to here, but you'll get used to it, I promise. Don't panic. Just to show you, the two big groups here are this, which is a conjunction, and this, which is a single letter. Okay, so the first thing we do is we make our branches. Again, it'll occur a lot of the time that you have schemata with letters that are tied for the most frequent. So let's start with A just because. So that's true or B and not B, therefore true, right? Whole thing's a conditional, put our dots in. And on the other side we have false or B and not B, therefore false. Okay, so let's look at the left side first. Well, I can think of two rules that we could apply. We could do something with the alternation in the first part. I mean, that would be perfectly legitimate. There's nothing wrong with doing that. But if we notice that our whole schema is a conditional, then we see that the whole schema is a conditional with a true consequent. And remember, our sixth rule, I think, lets us reduce a conditional with a true, with a true consequent to true. So this just goes to true, right? So what do we do over here? Well, there are a few things we could do. So the whole thing is a conditional. So let's see what we can do about this first. So if we look at rule 7, right, this whole thing's a conditional and it has a false consequent, right? So rule 7 tells us that if a conditional has a false consequent, you reduce the whole to the negation of the antecedent. So what that would look like is negation sign, false or B and not B, right? And again, this is the antecedent, so we negate that. So we can apply another reduction rule involving alternation, right? So we drop false as a component of alternation. So that leaves us with not B and not B, right? Now, and we could also get rid of the dot if we wanted to. So you could branch this again if you really wanted to, but because it was one of the examples of an inconsistent schema, you might notice that B and not B can never be true. It's always going to be false. So what I would do here to save some time is, I would just reduce this to not false, right? And that to true. If you ever run into, so that's the full truth value analysis, and it turns out that this schema is valid. Woo. We got a valid schema. Okay. So if you ever, just for a second so you can pause to see the whole thing. So if you ever have a schema like P and not P, right? Or, if it's like P and Q and not P, right? So these, both schemata like this, and schemata like this, they're always going to be false. Any conjunction that contains a single letter and its negation is always going to be false. So for both of these, I think it would be okay to just save time, reduce that to false, or reduce that to false. Similarly, if you have an alternation of P or not P, right, that's always going to be true. Again, that was sort of one of the examples of a valid schema. So anywhere in a truth value analysis where you have something like P or not P, or even like P or Q or not P, right, that's going to go to true, and that's going to go to true. That's just a shortcut you can take. You don't have to, but it does save you a lot of time, so it's good to get kind of used to that. Okay, so let's try one more. I think this is the fourth one. Right, so let's do not P or R if and only if P, therefore R. Actually, I'm going to negate this whole thing. Right, Okay, so again, we have the tied number of letters. Again, that's probably going to happen the vast majority of the time. I'm just going to start with P. So on the left branch, I'm going to assign true to P, but remember, that means I have to keep track and make sure that not P comes out false. So how that looks is negation, then false, because we're assigning true to P, so not P is false, or R. And again, I'm using more dots than are strictly speaking necessary. That's just to make things a little clearer for y'all. True, therefore R. Right, I'm just going to do the left branch, then I'll come back and do the right one. Okay, so we've plugged in true for P, which made not P false, right? So what do we want to do? So here on the left side, we have an alternation. On the right side, we have a conditional, right? So we could apply a few of our rules to this schema, right? So first, just because it's a nice, simple, easy one to remember, what I'm going to do is I'm going to drop the false as a component of alternation here. So R, if and only if, true, therefore R, right? Cool. So what do we do now with this schema that we have left over? Well, if we look at our rules for conditionals, right, the right side of this biconditional is a conditional. So if we look at the rules for conditionals, we will see that rule 5 tells us to drop true as the antecedent of a conditional, right? So that gives us not R if and only if R, right? I just got rid of the dots because they don't do anything there. You can keep them. It will never screw anything up if you keep the dots. I just like things to be neat and tidy, sort of. Okay, so what do we do here? So we could branch this again. So I'll just do it the long way and then explain why you shouldn't do it the long way if you can avoid it. So we get not true if and only if true, and not false if and only if, well, that's awful. I really can't draw these arrows. If and only if false, right? And we could go to our biconditional rules and, you know, I'll just do it once. I'm not really ever going to do this again this way. So we could apply our 8th rule, I believe, to drop true as a component of a biconditional, and that gives us not true. We can only drop one at a time. We can't like make it disappear into nothingness, right? So if we have a biconditional where both sides are true, we drop one of them and just reduces the whole thing to true. And right, the negation of something that's true is false, right? So that's going to end up false. So here, well, what do we do here? We have a biconditional with a negation on both sides. So we apply our rule 9, where we drop false as a component of a biconditional and then negate the other side, right? So this will be, this is annoying, but false, right? So then we can apply, we can apply our negations. So we don't strictly speaking have rules for negation. It's just it switches the truth value of what's inside of it. So this would go into not true, and not true is false. So that's one side of it. Now, the reason why I say that you should never do this is because it takes a lot of time that you could be spending doing more fun things, like not logic. So what I would do here is, we know that a biconditional with the exact literal same thing on both sides is always going to be true. So, because they'll always have the same truth value, right? So that would be not true, and that goes to false. Again, that saves us a considerable amount of time. Gets us the same place we wanted to go, but faster. Okay. So let's draw my thing to keep the branches separate. So we made P true in the left branch, right? So here we're going to make P false, which remember we'll make not P true. So the not P here is true because P is going to be false. True or R. Let's zoom in actually. Oh, wait, I need to see my thing. So I'm going to space that a little bit. True or R. If and only if. False, therefore R. Sorry, I'm running out of space here. I could zoom in more, I guess. I do have an iPad. Okay. So what do we do here? And again, we have two sides. Again, one side is an alternation. The other side is a conditional, right? You can do these one at a time, or you can skip like one or two steps. I don't really mind if you do two things to one line at once. I will definitely recognize it. So I'm just going to do the stuff with the conditional right here first. So what I'm going to do is negation sign, true or R, or lowercase r, if and only if, false, or wait, sorry. So what I'm going to do is I'm going to reduce this whole conditional right here to true, because any conditional with a false antecedent is true, right? So true. Okay, now we got to look at our alternation. So what do we do with our alternation? Well, we know that an alternation with at least one component that's true comes out true as a whole. So not true if and only if true. And so again, you could just recognize that this is going to reduce to true, but if you want to go through the rules in detail, so you drop true as you drop true as a component of a biconditional, right? So you get not true, and not true is false. So this is the truth value analysis, so I haven't made any mistakes for this schema, and interestingly, because it always ends in false, the schema is inconsistent. Okay, so I hope that that gives you enough of an example to start doing these. What I'm probably going to do is after you hand in your homework for this chapter, I'm just going to do all of the homework problems like this, where I explain kind of how every step works. And again, if you're confused about this, like you're trying an exercise and you just don't get it, send me an email. It takes me 3 minutes to record a video of me doing one of these, right? And I think it'll be helpful for you and everybody if one of them is particularly tricky. Okay, that is all for, well, I think that's all for chapter 3. Let me double check. Or chapter 4. Yes, that is all for chapter 4. Please try the exercises. Please try to get pretty good at this. Again, it's going to be really important going forward, but I don't think it's all that bad. And I think if you give it a shot, you will do fine. See you next week.